Hello there! This lecture is going to show you how to apply all the conceptual things that you learned in the previous lecture about the sampling distribution and the standard error. We're going to be looking at computing Z and T scores based on the standard error, and then making decisions in business-related scenarios based on some research and findings and comparing those findings to the standard errors using your Z and T scores.
So we're going to start with a brief recap of research methods because we are going to be now talking about situations where research has taken place and we're evaluating the results of that research. So this is stuff that we covered a long time ago and I just want to refresh your memory. Then we're going to recap the standard error and sampling distributions, which should still be pretty fresh in your mind because that happened just recently. Then recap z-scores for single values, which should also be relatively fresh in your mind. Then we're going to move on to z-scores for sample means. So slightly different concepts and formulas, but overall kind of the same gist of what was happening with z-scores for single values. Then I'm going to introduce you to t-scores for sample means, which is very similar to z-scores. It's just a situation where we either don't know anything about the population or don't care about the population, or we're comparing our sample to a population mean and we don't know the population standard deviation. Then we're going to talk a little bit about why I care about the standard error and Z or T scores for sample mean and demonstrate why you should care by showing how you can make decisions based on research using Z or T scores, which is heavily based on the standard error and looking at where your particular sample mean falls in a sampling distribution. So just as a quick recap of research methods, remember the independent variable is whatever is manipulated. It's the intervention. It is whatever the predictor is in the relationship that you're looking at between two variables. Or if you haven't manipulated anything in a study, like you haven't given training or given people a drug or tried a new management technique, or you haven't done anything physically or manipulated anything, the independent variable can also be the basis for group comparison. So maybe comparing job satisfaction between employees at a company undergoing layoffs versus employees at a company who are not undergoing layoffs and just comparing those two groups. Or comparing job security between those that are undergoing layoffs and those that are not, or between males and females, or between different departments or anything like that. The dependent variable is what a researcher actually measures. That's typically the scores that you're working with when you're doing data analysis, and it represents the outcome of that intervention, of whatever happened with that independent variable, or the outcome that's supposed to differ based on those group comparisons. And it's assumed to depend, dependent variable, on the independent variable. So you can kind of think IV independent variable leads to DV dependent variable. Also remember, a population is all people or items of interest. So as an industrial organizational psychologist, I'm interested in all employees for the majority of my studies, but typically I do research on who I have available to me. So either people who are willing to take my survey online or employees at Nevada State College, which would be my sample, right? So I'm interested in all employees, but I study who I have access to, who's realistic to measure, who I have the resources to actually study. That's my sample. And then I do research on that sample. And if I get findings that are make me confident that the relationships I observed or the differences I observed are actually really there, not just due to chance, then I can be confident that whatever I observed in my sample would probably be observed in my population, assuming that my sample is a pretty good representation of the population anyway. So let's think of an example because that always helps, and we'll use this example throughout the lecture. Let's say that a researcher wants to conduct a study on the impact of some sort of intervention on some sort of outcome of interest, right? So again, they can take a sample, manipulate the independent variable, and measure any changes in the dependent variable. Because again, the population is not usually feasible to obtain, and it's important to pilot interventions before any kind of wide-scale implementation. So before the researcher can be confident that any observed changes in their dependent variable in their sample was actually due to the independent variable, they need to know how likely their results would have been just due to chance. Again, that's the standard error, if you remember that concept. So just because you see a difference in the outcome, the dependent variable, after the intervention, the independent variable, does not guarantee that the differences are due to what you actually did in the study. Remember, those naturally occurring differences that occur just due to random chance or the standard error must be taken into account. So keep that in mind as we go through this next example. So let's say that Nevada State College develops a new training program for faculty to help them provide better feedback on written assignments. So before requiring it for all faculty, Human Resources randomly selects a sample of 30 faculty to participate in the training to pilot test it. So over the summer, the 30 faculty complete the training. Then they compare their feedback ratings, and you can see the measure of feedback ratings on your course evaluations below. They compare the feedback ratings of those 30 faculty to the typical mean feedback ratings for fall semester, so the population, to see if these trainees have much better ratings for feedback than the general population of faculty. So they're really looking to see if the ratings on these items, overall mean, is higher than the margin of error or chance compared to the population mean feedback ratings. So in this example, the independent variable would be the training. The dependent variable would be the feedback ratings, right, what we're measuring. The sample is the 30 trainees, and then the population is all faculty. So we're basically trying to see if this training program improves ratings for feedback in the sample, and if it does, and not only improves them, but improves them beyond what we would expect to see due to chance, right, beyond the standard error, then we could justify implementing this training to all NSC faculty. So now just a quick recap of the standard error and how it applies to the specific training and feedback rating example that we're going to use in the lecture. So remember, the sampling distribution is every possible sample mean of a specific sample size that could be randomly drawn from a specific population. So all of the possible sample means for the dependent variable that a researcher could have observed in the study if the independent variable had no effect, differences were just due to chance, and the sample still technically represents the original population who didn't receive the independent variable. So for example, in the example we're using, the sampling distribution would be all of the possible mean feedback evaluation ratings for any given sample of 30 faculty members from the original population who received no training. Or another way to think about it, all the possible mean feedback evaluation scores the researcher could have gotten if the training had no effect, right? The original population, what are all the possibilities the researcher could have got for any given sample of 30? Remember that the mean of the sampling distribution, or the mean of all possible sample means that the researcher could have gotten due to chance, is equal to mu, or the population mean. So this allows you to compare your specific sample mean to the population mean when using the sampling distribution to examine how likely the results observed in your study would have occurred due to chance. So related to our example, this is really the basis of comparison for your sample in the sampling distribution, because we're going to compare our sample mean to the mean feedback evaluation ratings of all possible sample means for any given sample of 30 faculty members. Luckily, this is the same as the original population mean for feedback evaluation ratings, so you can still compare your actual sample mean for feedback evaluation ratings to the ratings among the population of faculty who did not receive the training. Standard error. So remember, that is how far away you expect any randomly selected sample mean to be from the population mean just due to random chance. Or in other words, if the independent variable that you manipulated in your study did not really have an effect on the dependent variable, how much of a difference would you expect to see no matter what? Just naturally occurring differences have nothing to do with what you manipulated in your study, just differences due to chance. So this is the basis of comparison for the actual difference in the dependent variable observed after you manipulated something in your study. So for example, just because your sample of 30 trainees had a higher mean feedback evaluation rating, this does not necessarily show that the training was the reason for those higher ratings. You must be able to show that the difference in the mean feedback evaluation ratings between the sample of trainees and the original population, that difference has to be larger than the standard error or the difference expected due to random chance, even if the training had no effect. Because remember, even if that training had no effect and differences were just due to sampling error, you're still going to see some differences, right? Even if the training didn't work. So what you would do, again, compare the actual difference between the sample and the population mean to the standard error, specifically using a z-score or a t-score in certain circumstances to see how extreme your sample mean is. So remember when we looked at z-scores for x, we would say an extreme value would be any x value with a z-score of 2 or above or -2 or below. That's kind of the same criteria that we're going to use when we're evaluating how likely a sample mean could have occurred just due to chance and not really necessarily because of whatever you manipulated in your study. So before we jump into the z-scores for sample means, let's do a recap of the z-scores for single values that you've already seen. So remember, Z tells you how many standard deviations above or below the mean a particular score is. So you're comparing the actual difference between your score and the mean to the standard deviation, or the typical difference among all scores and the mean. So again, it tells you the distance in terms of standard deviations, and that distance is told to you by the actual numeric value. Again, you ignore positives and negatives, you just look at the absolute value. The larger the absolute value of your z-score is, so if it's like a 5 or -5, it's pretty large. Absolute value, remember -5 is not a small number here. It's a large difference, right? It's a large difference in terms of standard deviations. So if you have a larger z-score, absolute value, that means that the score you're actually looking at, the score that the z-score was used from, is further from the mean. It's more extreme or more rare. If we have a normal sampling or a normal distribution here, you're looking at something that's either further out here or further out here, very unlikely. So our criteria for extreme is any value that has a z-score less than -2 or less, or +2 or more, meaning that it's at least 2 standard deviations away from the mean. Smaller z-scores mean that x is closer to the mean, so something kind of like in this little region here. Remember, 0 is in the middle, so the closer that your z-score is to 0, or in other words, the smaller your absolute value of your z-score is, the closer your value is to the mean. It's a more common value, higher frequency. Direction. So that's told to you by the sign. Now we're not ignoring positive and negatives anymore. We care about positive and negatives. And the direction tells you, is the score above or below the mean? If you have a score that's equal to the mean, then the z-score is 0, because then that score is 0 standard deviations away from the mean, because it's equal to the mean. If you have a score that's above the mean, over here, it's going to be a positive value. If you have a score that is below the mean, you're going to have a negative value, and those are to the left of the mean. Think about the formula for this. If your score is greater than the mean, you're going to have a positive value because you're going to have a larger number minus a smaller number. If your score is less than the mean, you're going to have a smaller number minus a larger number, and that's going to give you a negative z-score. So that should make sense mathematically as well. Notice that the formula for the population and sample, pretty much the same, just difference in notation. Score minus mean divided by standard deviation. Then remember, you could convert z-scores into x values using these formulas that you see here as well. So now we're going to use kind of the same template for the recap of z-scores for single scores, but now we're looking at sample means, and the underlined stuff is different from the z-scores for x. So a lot of this is the same, but the underlined stuff is what has changed now that we're talking about z-scores for sample means and not z-scores for single values or for x values. So now, instead of telling you how many standard deviations above or below the mean a particular score is, Z is going to tell you how many standard errors, or the typical difference between any given sample mean and the population mean, how many of those above or below the population mean is a particular sample mean, not a score. Now our distance is in terms of standard errors. But when we talk about distance, we still ignore positives and negatives. So the larger your z-score is, the further away that particular sample mean is from the population mean. It's more extreme. It's more rare. If we actually took a sample, manipulated them, and then they got a large z-score, that means it's not likely that we got that mean due to chance. It's rare that it would occur due to chance. So we could be confident that it's actually probably due to what we manipulated, and that mean isn't something that would have been in the sampling distribution from the original population. Our criteria for extreme is still the same. So if we get a z-score in our sample that we manipulated, like if we took the sample of trainees and their feedback evaluation score gave us a z-score of 2 or higher, we're feeling pretty darn good that it's the training that led to that difference and not chance, because that is a mean that's unlikely to occur due to chance. It's extremely high. And just like z-scores for single scores, a smaller absolute value of a z-score means that your value is closer to the middle, or in this case, your sample mean is closer to the population mean. It's more common, it's likely due to chance. So if we did the training example and we got a z-score around 1, it's positive, so that's cool, but I'm not feeling that confident that that difference is actually due to the training, because it's pretty darn close to what we would expect to see just due to random chance. It's a common value that would occur due to chance, not necessarily due to the training. Yet again, the direction is told to you by the sign of the z-score. So it's, instead of comparing a score to a mean, we're comparing a sample mean to a population mean. If your sample mean is equal to the population mean, z is 0. If your sample mean is above the population mean, it's positive. And if your sample mean is below the population mean, your z-score is negative. Here is the z-score formula for the mean and the sampling distribution. You will see that the x is replaced with an x bar. This is still a mu, population mean, and the standard deviation is now replaced with the standard error. This is an equivalent version of the formula. I just broke down the mean, sample mean formula for you here, and that formula for standard error that you saw in the previous lecture. So now let's take a look at the concepts and formulas behind t-scores. Now these are very similar to what I just showed you for z-scores for sample means, except now we can work with t-scores when we have a situation where we're comparing the sample mean to a population mean, but we don't know the population standard deviation. So instead, we estimate that population standard deviation using the sample scores. We just take those sample scores, compute a sample standard deviation, and use that to estimate the true spread of scores in the population. So when we're looking at t-scores, we don't necessarily have the standard error, we have the estimated standard error. Also, t works when you want to compare your sample mean to a specific value instead of actual population values. So if you have a certain sales goal and you want to compare your sales after an ad campaign to the goal, you're not going to have a population standard deviation, but you can replace that mu, that population mean in your formula, with your goal value, and then use the sample standard deviation from your actual data to compute your standard error. So in sum, t really works great for situations when you don't know the population standard deviation, or you want to compare your sample to some sort of predetermined value. So in that case, again, the population mean would be replaced with that predetermined value of interest, and then that standard error is computed with the sample standard deviation. So for instance, let's say that we had a goal for faculty to get excellent ratings of 4.5 plus for feedback. So instead of comparing our sample to the population mean to see if they're now different from the population, we would compare our sample to the goal to see if they reach the goal beyond the margin of error, beyond the standard error. So our mu would be 4.5 and we wouldn't have a population standard deviation. So we would estimate it with the sample standard deviation. Also, when it comes to the sampling distribution, for t to be normal, you need to have a sample size of at least 121. This is because there's more variability now. Back in the past, when we looked at all the possible z-scores, the only thing that changed from one z-score to the next was the sample mean. But now, we're going to have not only would our sample mean change for each possible sample mean for t, but also the standard error will change because each mean or each sample is going to have a different standard deviation, which is going to give us a different standard error. That's not critical. It's true, but it's not something you have to really focus on. I just wanted to point that out so you don't think that the two sampling distributions function in the same way. For our purposes, I'm always going to make sure we're working with normal distributions. So let's take a look at our formulas. Here you can see that the numerator is the same for z, but now instead of having a little sigma, a little funky looking O for the standard error, we have an S because we're estimating it with the sample standard deviation. So again, this is the equivalent formula, just broken down more. Here's the formula for the sample mean. Here's the formula for the standard error using the sample standard deviation, which you can find the formula for right here, just in case you forgot what it looks like. Again, this is an equivalent formula to the previous one. It's just now we've broken down the formula for the sum of squares right here. Don't worry, I'm not as worried about the math as I am about the concepts. So why the heck do we care about the standard error or z-scores and t-scores for sample means? So if you want to examine the impact of an independent variable, an intervention, manipulation, or group difference on the dependent variable, right, some outcome of interest, then you can't just simply compare your sample mean and your population mean. It's not good enough. Simply observing those differences in the outcome is not enough because differences can occur just due to chance, not necessarily because of what you did in your study. So you have to consider the differences in outcomes that could have occurred due to chance, the standard error, right? You have to compare that actual difference to the difference that you would have seen even if your intervention, manipulation, or group difference, your independent variable, had no effect on your dependent variable. So you have to compare that to the margin of error or the standard error. So you would ask yourself in our example, does the improvement in feedback evaluation ratings for trainees exceed the standard error? Or is this a rare sample mean among all possible sample means that could have occurred just due to random chance, even if the training had no effect? All right, so now the fun part, we actually get to do some examples looking at evaluating the effectiveness of an intervention on a dependent variable, or in this case, looking at how well this training actually impacted or improved the evaluation ratings for feedback among faculty. So we start off by looking at the overall statistics for feedback evaluation ratings. So in the population, we saw that the overall mean for those evaluation ratings was a 4.2 with a standard deviation of 0.55. So on average, most people get within 0.55 points of a 4.2 in the population. Now we've got our sample of 30 trainees, and we find that they have a mean feedback evaluation rating of 4.4. So at this point, we're feeling encouraged, right? We're like, oh, cool. Their rating was higher, right? The trainees had a better rating, but we don't know if that's meaningfully better until we compare that 0.2 point difference to the difference we'd expect to see even if the training didn't work and differences were just due to chance. Or in other words, we have to compare this 0.2 point difference between the population and the sample mean to the standard error. So to compute the standard error, you take that standard deviation of 0.55 right here, divided by the square root of your sample size of 30. And you end up getting 0.55 divided by 5.478 and a standard error of 0.1. So now we're going to use a z-score to see how much of a difference we observed, how much bigger that difference we observed is compared to the difference expected due to chance. So we plug in our sample mean of 4.4, our population mean of 4.2, and the standard error that we just computed of 0.1. And we find that the actual difference in feedback evaluation ratings is 2 times better than the difference we would expect to see just due to chance. This is super impressive. We're feeling good. Now let's go ahead and visualize this distribution and kind of where this sample mean would actually fall. So we're going to draw this out and start getting in the practice of doing this, especially when we start doing probability. So we're going to do a normal distribution, and I know it's normal no matter what the population looks like because I have a sample size of at least 30. So I'm going to go ahead and start by putting my my population mean of 4.2 in the middle. Now remember, This distribution represents all the possible sample means I could have gotten just due to chance, even if the training didn't work. And the mean of all the possible sample means is equal to the population mean. So that's why that goes in the middle. Now, when we talk about, and I'm going to put X bar here, talk about z-scores, remember the z-score for the mean is equal to 0 because 4.2 is 0.1 values away from the mean, or 0 standard errors from the mean. So if we just kind of do a rough sketch of where most scores are going, or where most sample means would fall due to chance, if I randomly took any 30 faculty members that didn't receive the training, and where would their mean probably fall? So 4.2 plus 0.1 gives me that 4.3 here. So that's going to be my z-score of +1. And then for my z-score of -1, we have 4.2 minus 0.1, which would be 4.1. So this is where most of those sample means would fall just due to chance. Now we look at our actual sample mean, and let's make that blue. That's a 4.4, and it had a z-score of 2. It is way out here, right? It's in a low frequency part of the distribution. It's in the far right of the sampling distribution. It's very unlikely that we probably would have gotten this sample mean with this z-score just due to random chance. It's way far out there, right? So remember, this distribution represents all of the frequencies, right? The height of the little curve, all the possible frequencies for every single possible sample mean the researcher could have gotten due to chance, not training, from the population. So it makes sense that we want our sample to be extremely rare in this distribution because we don't want our sample mean to represent a likely possibility that the researcher could have gotten due to chance. So based on this data, we're confident that the training led to this difference in mean feedback evaluation scores because it's not likely we would have gotten this sample mean if the training didn't work and differences were just due to error or chance. Hooray! Now let's look at an example where we still have the same population and sample mean. We still have a 0.2 point difference in feedback evaluation ratings between the faculty and the population and the faculty who received the training. But now we have a larger standard deviation in our population. The spread of those ratings is larger. So now we know, let's see, that roughly most people get between a 3.4 and a 5 in the population. So 4.2 plus or minus 0.8. So pretty huge spread of scores in the population for feedback evaluation ratings. So now let's evaluate again. Is that 0.2 point difference in feedback evaluation ratings substantial compared to the difference we'd expect to see no matter what, just due to chance? Here's our standard error, right? So now we can compare that 0.2 point difference to the 0.146 point difference we'd expect to see no matter what, just due to naturally occurring differences that happen between samples and populations that have nothing to do with training. So we compare our actual difference to the difference we would expect to see just due to chance, and we find that just based on the z-score, we know that the mean feedback evaluation score among the 30 trainees was 1.37 times better than the difference expected just due to chance. This is good, but it's not super impressive or extreme. So just to hone in on this, let's go ahead and draw or visualize this distribution. So, because drawing is good. We got our normal curve. Our sample size is big enough to be confident our sampling distribution is normal. We put our population mean right in the middle, and that always has a z-score of 0. Okay? Now, if we think about just kind of roughly where most sample means would fall due to chance within one standard error of the population mean, on the right side, for a z-score of 1, we would have 4.2 population mean plus 0.146 standard error, and you would end up getting 4.346. For a z-score of -1, well, what sample mean would be one standard error below the population mean, or in other words, 4.2, the population mean, minus the standard error of 0.146, you get 4.054. And our z-score here, we're going to make it black, of our sample mean would be right about here-ish, right? So just due to chance, most of our sample means will fall between 4.054 and 4.346. So this sample mean of 4.4, I'm kind of out of room here, it'd be like 1.37, 4.4. It's not super likely, right? It's in the rare side, but I don't know if I'm super confident, right? It's in the right side of the sampling distribution, but it's not that rare or extreme. So we're somewhat confident that the training led to this difference in mean feedback evaluation scores, but if the training is time consuming or costly, it may not be worth implementing because it didn't have an extreme impact. So now we're going to do an example looking at t-scores for the sample mean. And so here, remember to use t, we either have a situation where we're comparing our sample to a population mean, but we don't know the population standard deviation, or as I'm going to demonstrate in this example, we're comparing our sample to a specific goal population mean. So let's say that the next semester, 6 more faculty participate in the training. So now there's 36 trainees total. And among those faculty and the faculty who participated in the first round of training, the mean feedback evaluation rating is a 4.65 with a standard deviation of 0.95. And let's say this time we don't really care about the population parameters. We just wanted the training to result in a sample mean feedback evaluation rating that was meaningfully above the 4.5 criteria for excellent ratings in faculty annual performance reviews so that we could be confident that NSC leadership would know that implementing the training would get the population mean of all faculty in the excellent 4.5 or above range. So what we need to do is see if the sample mean is far more than the standard error above 4.5. So to see if this difference between 4.65 and 4.5 or 0.15 points is meaningful, we would compare that to the standard error of 0.158. And remember, this would be the difference you'd expect to see just due to chance, even if the training had no effect. And this is estimated based on the sample standard deviation. Now we look at the t-score for trainees, and we find that the actual difference between the sample mean and the goal, or 0.15, is 0.949 times larger than the difference we would expect to see just due to random chance. So it's okay, but it's still kind of within the margin of error. So it's not really clear if the mean feedback evaluation rating is meaningfully above that 4.5 criteria for excellent ratings. So NSC may not be as confident that implementing the training would get the population mean of faculty above that or in that range. So it's still within the realm of likely possibilities due to chance. It's still within one standard error of the mean. But let's go ahead and visualize this sampling distribution because it helps, and drawing pictures is great. All right, here we go. Normal curve. We're assuming that the ratings are normally distributed in the population because now we're working with T, and this sample size isn't good enough to get us to a guaranteed normal sampling distribution. So we're assuming that the scores are normal in the population. All right, here we go. In the middle, now goes our expectation, what we replaced mu with in our formula. That's 4.5. Bam. Okay. And the error that we would expect of 4.5 is that 0.158. Again, this is going to be a t of 0, x bar here. So for a t-score of 1, we take 4.5 plus the standard error of 0.158, and we get 4.658. 4.658. And for the low end here of the expected means due to chance, we take 4.5 minus -1 or minus 1 standard error. So 4.5 minus 0.158, we get 4.342. Okay, so that's where, due to chance, most means would fall if we were meeting our goal of 4.5. So we look at this and we go, okay, well, we'll use blue. Our mean was 4.65, which is like right here, with a t-score of 0.95-ish. And it's within the realm of possibilities that we would expect to see if we were meeting our goal, but results were really just due to chance, not necessarily due to the training. But this is encouraging because it wouldn't be too difficult to bump that sample mean into this territory where we're feeling really good that it's actually the training that would get us there. All right, so I hope you've enjoyed learning about how to apply the sampling distribution and the standard error to evaluating the effectiveness of interventions and research to make decisions based on data and be really confident that any differences or effects that you observe are actually due to what you think it's due to and not just due to random chance or the sampling error or the standard error value.